right, well, we're going to get into a new kind of area for this class. So we're going to start talking about probability. So the next few chapters are all probability. They're really building on each other. And so this chapter is kind of just the basic things and to kind of get us introduced to some of these ideas. And then as we go along, things will get a little bit more complicated. I don't think they get too complicated in this class. But in the past, students have had trouble with these probability chapters. And part of the reason, I think, is there are a lot of different types of problems. And one thing that students seem to have trouble with is knowing when do you use which technique. So what technique are you supposed to use for whatever type of problem that you're looking at? So as you're doing homework and as I'm working through these examples, try to pay attention to what is different from other types of problems. Like try to pay attention to the differences because none of these require a lot of work. Like we're not going to have, none of these problems require a half a page of, calculations and things like that. These are all very short problems as long as you know how to approach them. And so that's really, I think, the big stumbling block for these is just getting started. And so the more you practice it, the more you will see kind of the repetition and see the words that are common for these, whatever type of problem it is. And the more you do that, the easier this will get. And so I would encourage you to practice these a lot, just because it really will make things a lot easier. So let's just start with some vocabulary. So we have trial. Trial is just occasion where we observe a random phenomena with, for example, flipping two coins. Outcome is the value of the trial, so heads or tails for each flip. And then the event is the combination of the trial's outcomes. So we're flipping two coins, so we could get heads and then tails. Sample space is just a collection of all the possible outcomes. So if you're flipping two coins, the sample space would be heads, 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 tails, tails, heads, and then tails, tails. So we'll kind of use those. It's not super important that you memorize those definitions or anything, but when we say sample space, for sure you need to know what that means, and then kind of just be vaguely aware of the difference between trial and outcome event, and you'll be fine. So law of large numbers. So if you flip a coin once, so if you flip a coin once, you either get 100% heads or 100% tails. So obviously we know that if you flip a coin, the probability you get heads is 50%. But if you only flip it once, you cannot get 50% heads. You either get all heads or you get all tails. Or we could say 100% heads or 0% heads. And maybe we'll say that instead, 0% heads, although it's saying the same thing. But you either get all heads or you get no heads if you're only flipping the coin once. But if you flip the coin 1,000 times, you will probably get around 50% heads. And that's what the law of large numbers is saying. So the law of large numbers states that for many trials, the proportion of times an event occurs settles to one number. So as you flip the coin more and more and more times, the number of heads that you've gotten over however many flips you've done will come down to around 50%. And probably eventually, if you took that to infinity, it would be exactly 50%. But it's going to be around that. And the bigger the number, the more times you flip it, the closer it is to 50%. So that's what the law of large numbers states. So that's called empirical probability. Law of large numbers requirements. Identical probabilities, so the probability of each event must remain the same for each trial. And then independence, which we're going to talk a lot more about we'll talk a little bit later in this chapter, but we're going to talk a lot more in chapter 13. The outcome of the trial is not influenced by the outcomes of the previous trial. So in other words, whether you got heads or tails on the first flip, it's still a 50-50 chance of getting heads on the second flip. It's not going to change. An example of events that would not be independent. Let's say you have 30 people in a classroom and you're going to randomly pick 10 people. So you randomly pick the first person. If you're in the class, there's a 1 in 30 chance that you will get picked. And let's say you don't get picked, then we're going to pick someone else. And then let's say the first person comes out to the front of the room, so they're no longer in the pool to get picked. Then the probability you get picked the next time would be 1 in 29. So now it's changed from 1 out of 30 to 1 out of 29 because you took one person out. So that would be an example where the events are not independent because it's changing as you pick people in that case and they are coming out. The chances that you get picked next is getting more and more likely. So empirical probability just states, so we have the probability of event A. So we use a capital P for probability, and then usually capital letters, but we'll just kind of, a lot of times we'll probably just kind of briefly describe what we're talking about, but just in general, we'll just say the probability of event A is the number of times A occurs over the number of trials. And of course, this is in the long run. So this is over many, many trials. This is what we see. All right, now we have something called the non-existent law, the law of averages, which it doesn't really exist. People will kind of speak in these ways, but this is not really the right way to think about it. For example, if you flip a coin 6 times and you get 6 heads, then you're due to get tails on the next flip. That's obviously not correct because, like I just said, whatever you get on the first, I said first flip earlier, but the first 6 flips does not affect what you get on the 7th flip. So it's still going to be a 50% chance. You still have 2 outcomes. They're equally likely. So one half for the probability you get tails on the next flip. You put 10 quarters in the slot machine, you lose each time. You're just a bad luck person, so you have a smaller chance of winning on the 11th try. That's also not true. The slot machine presumably would have the same probability of getting any combination on any given time. So you're equally likely to lose every time. So there's no such thing as the law of averages for short runs. And to say that another way, if you flip a coin 10 times or whatever it is, whatever random thing you're doing, you could get 10 heads, you could get 9 heads, you could get 8 heads, you could get 0 heads. Like over a short number of trials, anything could literally happen. But again, if you flip a coin 1,000 times, you are not going to get 1,000 heads. It's just not going to happen. You will be close to that 50%. So over the long run, things balance out. Law of averages does not work because it's just kind of assuming that probabilities are changing when they're really not. All right, so let's talk about theoretical probability. So find the probability of drawing a face card, which is a jack, queen, or king from a regular deck of cards. So if you're not familiar with cards, there are 52 cards. There are 4 suits. So the suits are the spades, clubs, hearts, and diamonds. You have 3 of these face cards per suit. So times 3 face cards. So that would be 12 face cards altogether. So 12 out of 52 would be the probability you get a face card. So we say 12 face cards over 52 cards. And so that would be our probability. And normally, I think we'll say this in a second. Normally we write these as decimals, not fractions, but on the notes, I will, if it's easier, I'm not going to convert to decimals because you know how to do that. Flip 2 coins, show the probability or find the probability that both show heads. So let's list the sample space again. We did this on the first page, but if you're flipping two coins, and assume you can tell the difference. So let's say you have a quarter and a dime, so you can tell which one's first and which one's second. Then the sample space would be heads, heads. We have heads, tails. We have tails, heads, and tails, tails. So the probability that both show heads, we have one event that we're interested in. We have 4 events that we're not interested in. And that is 1/4. So what is wrong with this logic? Randomly pick 2 people, find the probability that both are left-handed. Sample space is left, 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 right, right, left, right, right. So the probability of getting both left-handed is 1/4. Well, that does not work because left-handed people are way more uncommon than right-handed people. It's not probability of 50% that you get right-handed. The probability is way higher that you get right-handed. Whereas in this case, the probability of heads and tails is the same. So we can assume each of these events are equally likely. We cannot assume these events are equally likely. You're not likely to get 2 left-handed people. You're much more likely to get 2 right-handed people. So that this kind of thing only works if the probabilities are equally likely. So when they're not, there's a different way to do it that we have not talked about yet. So, and that's a very common mistake, is assuming things are equally likely when there's no reason to think that, or in fact, it's given to you that they're not equally likely. So try to never assume that. Try to train yourself to not assume that things are equally likely, because most of the time they aren't. All right, so let's talk about formal probability. So the first rule is, and I think we probably all know this, the probability of any event A is always between 0 and 1. And of course, if the probability of an event is 0, that means that it's impossible. The probability of an event A is 1 means that it is 100% or certain to happen. Probabilities are normally written in decimals, so I may write them in fractions in the notes, but on any kind of assignment, you're going to write them as decimals. And then rule 2, the probability of S equals 1, and S, of course, like we said on the first page, is the sample space, and all that means is if you flip a coin, it's going to land on something. It's either heads or tails in that case. If you roll a die, it's going to land on 1 or 2 or 3 or 4 or 5 or 6 or however many sides that it has. It's going to land on something. So the probability it lands on something is 1. So that's all that one is saying. All right, complement rules. Now we're kind of getting in. These are a little bit more useful, and maybe not have seen these. So the complement rules. So a complement is the event where A does not happen. So it's all the possibilities where A does not happen. So if A is the event of rolling a 5 on a 6-sided die, then a complement is the event of not rolling a 5, or to say it another way, to roll a 1, 2, 3, 4, or 6. So rolling anything besides a 5, that would be a complement. So what's the probability of a complement? Well, either A happens, in which case you're at A, or A does not happen, in which case you're at A complement. So either today is Wednesday or today is not Wednesday. One of those 2 things has to be true. So we could say that the probability of A plus the probability of A complement would have to equal 1, because either A happens or A does not happen. There's no third option there, and the probability of everything is 1. So the probability of A plus the probability of A complement is 1. Let's rearrange this equation, and we get the probability of A complement equals 1 minus the probability of A. So the probability of rolling a 5 is 1/6. The probability of not rolling a 5 would be 1 minus 1/6, which would be 5/6. So the probability of A in this case is 1/6. The probability of A complement is 5/6. And we can see that these are all equally likely. We have 5 possibilities. There are 6 altogether, so 5 out of 6 versus 1 out of 6 for A. And that's another good thing you want to be able to do is be able to think of what the opposite would be. So if you have an event, what will be the complement of that event? You want to be able to do that. And we don't get, it's never that complicated. It's never too hard to think of it, but you do need to practice it, I think, because some people do have a little bit of trouble thinking in that way. So whenever you're given that opportunity, and we'll have some opportunities here, try to do that for yourself. So in this case, probability of green is 0.35. What's the probability of not green? So that would, of course, be, so the probability of, and we'll write green complement for not green. So that would be 1 minus the probability of green. And of course, that is 0.65. Okay, so complement just means opposite. And so let's talk about rule 4, which is the addition rule. So the addition rule says if A and B are disjoint, then the probability of A or B equals the probability of A plus the probability of B. And we'll talk about what disjoint means in a minute. But for this, I want you to write or implies add. So if you ever have an or problem, it always means add. Now, we'll talk in the next chapter, what if they're not disjoint. But for now, the problems you'll see in this chapter, you can assume they're disjoint, but we'll talk about why they're disjoint. And let's define what disjoint even means first. So A and B are disjoint if they have no common outcomes. Have no common outcomes. Or to state this in terms of probability, the probability of A and B equals 0. All right. To state it another way, A and B cannot happen at the same time in the same way. So, like for instance, either today is Wednesday or today is Thursday, but today cannot be Wednesday and Thursday at the same time. So the Wednesday and Thursday would be disjoint events. So here's an example. Number 4, probability of sophomore is 0.2, probability of junior is 0.3. Find the probability of sophomore or junior. These are disjoint events because you cannot be a sophomore and a junior at the same time. So disjoint events. So we can just add these. So the probability of sophomore or junior, we just need to find the probability of sophomore plus probability of junior. And so that is 0.2 plus 0.3, which of course is 0.5. All right, probability of green and yellow, and find the probability of red. So we're talking about traffic lights here, wasn't obvious. So in this case, we can use the complement because traffic light is either green or yellow or red. They are disjoint. It's never 2 colors at the same time. At least I've never seen that happen. And so we can actually use the complement. So probability of green plus the probability of yellow plus the probability of red would have to equal 1. So if we do 1 minus the other 2, then that would give us what we are looking for. So this is 1 minus 0.35 minus 0.04, and I think we get 0.61. All right, sum of probabilities, the sum of probabilities, and probably you probably know this, but if we talk about the sample space, you have all the possibilities, you add all those probabilities in the sample space up, has equal 1. So sum of probabilities must be 1. What is wrong with the following statement? The probabilities for freshman, sophomore, junior, senior are 0.25, 0.23, 0.22, 0.20. What is wrong with that? Well, 0.25 plus 0.23 plus 0.22 plus 0.20 would be 48, and that would be 42. So 48 plus 42, I think, is 0.90, and that is not 1. And obviously these are the 4 possibilities, and so all 4 of these should equal 1, which they don't. So how about the following? Probability of owning a smartphone is 0.5, probability of owning a computer is 0.9. These do not add up to 1, but this is okay because these are not disjoint. So you could own both a smartphone and a computer, and a lot of people do. So these are not disjoint, so you're not going to add those together. And just kind of as an aside, talking about disjoint events, if you have 2 or more disjoint events, so these 3 in this case are disjoint, these 2 are disjoint. If you add up probabilities for disjoint events, they cannot be more than 1. But if you add the probabilities for events that are not disjoint, they can be more than 1. So, and the further over 1 they are, the more overlap there is. But they could, if you have events that are not disjoint, it is possible that the probabilities add up to more than 1, and that would be okay. But if they are disjoint, meaning they cannot happen at the same time, then the probabilities cannot add up to more than 1. It could possibly be less than 1. So like if you add freshman, sophomore, junior, those are disjoint events, and you add the probabilities, they're going to be less than 1 because you still have 1 more category that you need to add in, which would be the seniors. And so that should take it to 1 if you get all the categories. But disjoint events, probabilities have to add up to 1 or less. If they're not disjoint, it could be anything. So it could be more than 1, it could be less than 1, it could be equal to 1, just depends. Okay, so we'll pick this up on the next video when we'll start with rule 5.